Okay, so we're now going to move on to a specific discrete distribution, which is called the binomial distribution. So this is a very specific binomial distribution, and something can be modelled as a binomial in very distinct cases. So if there are a set number of trials or a particular sample size, which we call n, if there are two possible outcomes, one that we call success and one that we call failure, and if the trials are random and independent. So examples of this are for when we've done GCSE and we've looked at probability trees and we've done rolling a 6 or not rolling a 6. That could be modelled as a binomial distribution. So if you're looking at bulbs, it might be categorising a bulb as faulty or not faulty. So those are the kind of things that we would model a binomial distribution. But we're going to look a bit more in detail of how you calculate it and how we write it before we go into exactly how we use it and what it means. So to write something as a normal distribution, we would say a variable x is modelled as a binomial distribution with sample size n and probability of success p. So how do I calculate a binomial probability? So I'm on to the next slide of my PowerPoint. Well, if we are finding a particular value, then we're actually going to go to individual cases of our binomial expansion. So we're going back to thinking about binomial expansion. So let's say we're looking at a biased dice. So x, which is the number on a biased dice, is binomially distributed. And let's say I roll the dice 20 times. And because it's biased, the probability of getting a 6 is a quarter. So I'm just going to write that explicitly. So the number rolled on a dice, and p is a quarter, which is the probability of getting a 6, because it's a biased dice. And I'll probably put that there. So let's say I wanted to know the probability of rolling 5 6s on a biased dice. So what that means is when I roll my dice 20 times, I'm going to get 5 6s and then 15 of any other number. So I'm going to get 5 6s and 15 of anything that's not a 6. Now, it doesn't matter what that number is because it's only a 6 that we are concerned by. So the probability of getting anything that isn't a 6 is 3/4. And obviously the probability of getting a 6 is 1/4. So if I'm getting 5 6s, then I'm doing 1/4 to the power of 5. And if I'm getting 15 of anything else, then I'm doing 3/4 to the power of 15. Now, I've assumed that I'm getting 5 6s in the first 5 rolls and then 15 6s. 15 not 6s. But it might be that I get 6, 6, 6, 6, 4, 5, 2, and then I get a 6 later on. I could get a number of different combinations where I get 5 6s. In order to do that, I would have to do my 20 choose 5. Because it's this that tells me how many different combinations of getting 5 6s and 15 of anything else is. So it's the probability of 6 5 times, or to the power of 5. Probability of not getting a 6, to the power of 15. 6 and a 6 and a 6 and a 6. That's why we're timesing it. All times by the number of possible combinations. If I were to do that on my calculator, 20 choose 5, which out of interest is 15,504. So that's why you're not going to be expected to write out all these different combinations. Multiplied by 1/4 to the power of 5 and by 3/4 to the power of 15. So to 3 significant figures, the probability of that is 0.202. So as a general form, the probability of x being a particular value, just move my pencil case out that way, sorry, is n choose r times by p to the power of r times by 1 minus p to the power of n minus r. So it's like an individual term in the binomial expansion is effectively what this relates to. Now the reality is you're not going to be expected to type this out every single time. The reality is that our calculators can do it for us. So we're going to do an example through together, which is on the next slide. So it's slide number 3 of the binomial section, number 7, I think, overall. We're going to do this example together and learn how to do this on the calculator. So a random variable x is binomially distributed with a sample size of 12 and a probability of success of 1/6. Find the probability that x is equal to 2. So if I were to do it long ways, I would do 12 choose 2, because I've got 12 trials, and I want to know out of those 12 trials, what's the likelihood that I'll actually only get 2 of whatever it is I'm finding, times by 1/6 to the power of 2, times by 5/6 to the power of 10. So this might be, I roll a dice 12 times, what's the probability that I get 2 6s? So it's 6 times 6 times not 6, 10 times, times by the number of ways that if I roll it 12 times, I'm going to get 2 6s. So, 12 choose 2 multiplied by 1/6 to the power of 2 times by 5/6 to the power of 10, which to 3 significant figures is 0.296 as a probability. Now to do it on the ClassWiz calculator. So you're going to go menu and you're going to go to number 7 distribution. There are loads and loads and loads of options. What we want is number 4 binomial PD. So P can mean parameter distribution. I like to call it particular, because then you know you're finding an equals, you're finding a particular value. So I think it's just an easy way of remembering it. So binomial PD. Now it gives you list and variable. We only want variable. So it asks you to type in x, n, and p. So x is the value that you are finding. So in this case, it's 2. N is the sample size. In this case, it is 12. And p is the probability of success. In this case, is 1/6. So once you've typed that in, you press equals, and it gives you the probability, which is exactly the same as what we've just worked out. So our calculator can do this all for us. So B, find the probability that x is equal to 9. So I'm going to do this straight onto my calculator. So as a reminder, I'm going to pick up my menu and I'm going to go to 7, I can't do it with that there, distribution. 7 distribution. Oh, sorry, I've lent on my calculator and I've put it in a weird mode. Right, there we go, back out of it. I'm then going to click for binomial PD because I'm finding a particular value. And then on my screen, I'm going to get list or variable, and I want variable. I'm going to have to type in x, which in this case it's 9 because it's the value that I'm looking for. N, which is 12 because it's the sample size. And P, which is 1/6, which is the probability of success. So it's there written down for you. Worth remembering, but I'll do it again on here. Menu, 7 distribution, binomial PD, variable, x is 9, n is 12, and probability is 1/6. So we get a number in standard form because our calculator gives it to us in standard form, but it means it's a very low probability. To be honest, that makes sense. The likelihood of getting 9 6s when you roll a dice 12 times is not going to be very high. So I can either write my answer as 1.26 times 10 to the minus 5 to 3 significant figures, or I could write 0.0000126 to 3 significant figures. Depends if you can remember how to convert to standard form. If you can't, writing that is an acceptable method. Okay, last one of this example. Part C is find the probability that x is less than or equal to 1. Well, now we have an inequality, but the only options where it's less than or equal to 1 are the probability that I get 1/6 or the probability that I get no 6s. So, on my calculator, on my distribution, I'm fortunate if I do not come out of the app, all my data from my previous question is in there. So if you're doing a question and you need to find multiple parts, it saves all the information for you. So I want to change x to be 1 and everything else can stay the same. So the probability of getting 1/6 is 0.26918. So I'm going to do it to more decimal places than I need. I'm always going to need 3 significant figures unless it says otherwise. So I'm just going to write 5 or so down so I definitely have plenty. And I'm going to do it again. And if I press equals after doing that, it just takes me straight back. So I want the probability of getting 0, which is 0.11216 to 5 significant figures. I'm then going to press menu and 1 because then it takes you back to my calculator screen and type those numbers in. So 0.26918 add 0.11216 is 0.381 to 3 significant figures. So using our calculator, these questions are really straightforward. So we're now going to go through a worded problem because that is more likely what you'll be expected to do. So the probability that a randomly chosen member of a reading group is left-handed is 0.15. A random sample of 20 members of the group is taken. Part A. Suggest a suitable model for the random variable x, the number of members in the sample who are left-handed. Justify your choice. So our suitable model is going to be the binomial distribution with a sample size of 20 and a probability of success, i.e. getting a left-handed person, of 0.15. Our justification is going back to what we did to start with. There is a set number of trials or a set sample size. There are only 2 possible outcomes, success and failure, so left-handed or right-handed. The trial is random and each one is independent. So me being left-handed wouldn't affect you being left-handed, for example. So this is what you need to write down for the justification of that question. Obviously not going to write it out again. So that would be our justification. B, use your model to calculate the probability that exactly 7 of the members in the sample are left-handed. So exactly 7 are left-handed. Menu 7, binomial PD, variable. So it's exactly 7, so x, the value I'm looking for is 7. N, the sample size is 20. There are 20 people in my reading group, and the probability of someone being left-handed is 0.15. So the probability of exactly 7 people being left-handed to 3 significant figures is 0.0160. And that's it. Number 2, the probability that fewer than 2 of the members in the sample are left-handed. But if it's fewer than 2, that means either one person is left-handed or no people are left-handed. So I'm going to go back, find the probability of one person being left-handed, which is 0.136798. I didn't want to use my 9 rounded, which is why I've done 6 significant figures. Press equals, go back and find the probability that nobody is left-handed, which is 0.0387595. Again, I could use slightly less significant figures, but I just want to make sure it's really accurate. So go back to my calculator screen and add these together. 0.0387595, which is 0.176 to 3 significant figures. Now in these questions, when you've had a fewer than, there's always been a small number. Now, more often than not, if they're going to ask you a fewer than, there's going to be quite a few more. And that's what I'll be doing in the next video, which is looking at a binomial distribution when we're looking at cumulative probabilities. So for now, I have selected 5 questions from the binomial distribution exercise, so that's 6b, that I would like you to work through. You can obviously have a go at others in your independent time, but for now, they're the ones that I want you to look through. And in the next video, we'll be doing cumulative probabilities.